Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 2, Newton's First Law of Motion, also known as the Law of Inertia. So in this unit, we're going to cover Aristotle's ideas of motion. Aristotle lived over 2,000 years ago, and he had his ideas about motion, which aren't really correct. And then we'll talk about how Galileo's concept of inertia revolutionized our idea about motion of objects in the universe. And then how that led to Newton's first law of motion. And Newton really codified, he came up with three laws of motion that really described how forces work in the universe. We'll talk about the concept of net force and vectors. And then we'll go to the equilibrium rule, and you'll learn that what we call mechanical equilibrium comes in two varieties: static equilibrium and dynamic equilibrium. We'll talk about the support force, also known as the normal force, and then equilibrium of moving things, and then finally the moving earth. So Aristotle's notion of motion was kind of interesting. In his time, he believed everything was composed of the elements of earth, water, air, and fire, those four elements, and that depending on which things were composed of, that will determine how that object will behave in terms of its motion. And every object that's not in its proper place will strive to be in its proper place. So, for example, he felt that since stones are made of earth, that they will drop to the earth. Puffs of smoke are made of air and fire, and they will rise like air and fire do. And rain will return to the sea, to the ocean. So because it's a type of water, and therefore will return back. So he felt that motion was determined on the basis of what things were made of. And so this was referred to as natural motion. So it was straight up and down things for all things on the earth, and beyond the earth, motion is circular. So, for example, a falling object will drop straight down. The sun and moon continually circle the earth, though remember, in these days, people thought the earth was the center of our solar system. We now know the sun is the center of our solar system, and that the earth revolves around the sun, and the moon revolves around the earth. He also thought there was a different type of motion besides this natural motion of things finding their natural place, what was called violent motion. And this isn't necessarily violent, but it's produced by external pushes or pulls. So there is a concept of force here, but he felt that you needed to always keep pushing an object with a force in order to keep it moving. In other words, once you stop giving it a force, it will stop moving. And we now know that that's not quite true. So in his world, in his worldview, shoving an object on the table will make it move the object, and wind will oppose the motion of the ships. Well, those are both true to a certain extent, but he was unaware of other forces like friction that were actually slowing things down. Friction of some object on a surface, on the ground, or friction between the air and an object moving, what we call drag or air resistance now. So Galileo lived in the 1500s, and he really demolished Aristotle's views about motion and how it worked. So he noticed that objects of completely different weight, about the same shape and size, but different weights. So say a stone ball or a metal ball and a wooden ball, and he would drop them from the Leaning Tower of Pisa. It was leaning even in his time, and he would hang over the edge and drop two balls of roughly the same size but very different weights, and he would see that they both landed at the same time. And so he felt that the moving object needed no force to keep it moving in this context. So force is what we call a push or a pull. And in everyday English, a push or a pull might not necessarily be a force, but in physics, a push or a pull that actually will change the acceleration, change the velocity of an object. That's force. So it will change the velocity, and velocity, we use velocity different from everyday English. In everyday English, we use speed and velocity to mean the same thing. Speed to a physicist is just how fast you're going. Velocity is how fast you're going and in which direction. So a force could change the speed and or change the direction, one, the other, or both. And inertia was a concept that Galileo created. This word inertia literally means inactive or sluggish. And it's a good idea to think of inertia as a sluggishness of all matter. It's a property of matter that makes matter resist movement. You have to give movement a force in order. You have to give matter a force in order to increase its speed or change its velocity. And it will depend on how much matter is in the object. So inertia is tightly related to the concept of mass, how much matter some object has. And it applies to moving objects, but it also applies to objects at rest. And this is an important concept in physics. So Galileo came upon these ideas of inertia by doing experiments with inclined planes. Inclined planes is just a fancy way of saying ramps, and he did ramps at different steepness. So he would change the angle and look at how the balls that he would roll down or roll up the ramps, how the speed would change over time as they're rolling. And he noticed that balls rolling down a downward slope will actually pick up speed. He noticed the acceleration that was caused by gravity pulling it down. He didn't call this gravity at the time, but he noticed this increase in speed as things were moving down ramps or being dropped. He also noticed when you roll balls up a ramp, they slow down. Obviously, eventually they'll slow down to a stop and then come rolling back. So a ball on a horizontal plane, in other words, just a flat surface, if you give it a push, it will maintain its speed indefinitely. Now, in practice, this doesn't happen because there is friction. There's friction between the ball and the ground that you're rolling it on, and there's friction between the ball and the air that the ball is moving through. But if you had a totally frictionless surface and you did this in a vacuum, in theory, the ball, once you give the ball a push, it'll keep moving until it runs out of place to move. And this is true also in deep space. You give something a push, there's no friction there. That object will continue on after it's accelerated up to a certain speed from the push. The moment the push stops, the ball will keep going, or the rock will keep going in space indefinitely. So these are two ideas that completely contradicted Aristotle's notion of motion. Okay, so a little quiz question. The use of inclined planes, ramps, for Galileo's experiments helped him to A, eliminate the acceleration of free fall. Free fall is when you just let something drop completely with the acceleration due to gravity, with no friction at all, even no air resistance. B, discover the concept of energy. C, discover the property called inertia. D, discover the concept of momentum, which we'll talk about in a later unit. Well, obviously it's inertia, that's what we just been talking about. The property of the inertia is a property of matter. It actually doesn't give an explanation about why matter behaves this way. It just happens to be a fact of what matter does. It resists movement. If it's already stopped, it's hard to make it move. If it's already moving in a constant direction and constant speed, it's hard to change that. So this led to Newton's first law of motion, the law of inertia. And Newton's law says every object will continue in a state of rest, that means stopping, or in a uniform speed in a straight line, what we call constant velocity, because it's constant speed and constant direction, unless acted on by a non-zero net force. In other words, by a force or a bunch of forces that don't add up to zero. They're real forces on an object. That's the only way to change the resting state or the uniform velocity state of an object. So if an object is affected by multiple forces that all cancel one out, we call that zero net force. Net force meaning the sum of all the forces in all the directions that might be pushing on that object. If they all add up to zero, say you have a force this way and a force this way, and pushing, they cancel, or you have one force this way and one force this way, they'll cancel. So you can imagine different combinations that will cancel. Those are called a zero net force. But if they don't cancel out, if you have a non-zero net force, an actual net force, the object will change velocity. It won't just have velocity, it will change its velocity. Its velocity will continue to change, what we call acceleration in the physics world. Now, I know we use acceleration in everyday English to mean going faster. But to a physicist, acceleration means going faster, going slower, or changing direction. Of acceleration to a physicist is any change in velocity. And remember, velocity has a direction as well as a size, a magnitude. So changing velocity can mean going faster, going slower, or changing direction. I like to joke with people that to everyday non-scientists, there's one accelerator in your car. But to a physicist, there are three accelerators in your car. There's the accelerator, the gas. There's the brake, because that will change your acceleration in a negative direction. And there's the steering wheel. They are all accelerators to a physicist. So there are a number of different units of measure that we use for force. And the classic one for the metric system and the international units system, the SI system, it's the International Système. It's in French, but it's abbreviated SI because that's the order of the words in French. It's a very closely related system to the metric system, and we're going to use the SI system for most of what we're doing here. Occasionally, we'll use the more familiar imperial system, what a lot of people call the English system, as well. But most of it will be in this metric/SI system. And the unit of force in this system is the Newton, named after Isaac Newton. This is a force required to accelerate 1 kilogram of mass. And if you want to imagine what 1 kilogram is, if you know what a liter looks like, it's about a quart. About a quart of water has a mass of 1 kilogram. So a kilogram of mass, if it's accelerated by 1 meter per second squared, what does that mean? 1 meter per second per second. So it's per second squared. That means that if you give it this force, if to a mass of 1 kilogram, at first it'll have zero speed, and after 1 second it will be 1 meter per second. After 2 seconds it will double to 2 meters per second. After 3 seconds, 3 meters per second. So you keep increasing the speed every second by 1 meter per second, what we call 1 meter per second, or 1 meter per second squared. That's just an acceleration that is used in the definition of meter. It is not the acceleration due to gravity. That is about 10 meters per second squared if you actually dropped an object. All right, so the unit 1 Newton is also equal to a related unit in a modified metric system called the CGS system, and it's equal to 100,000 dynes. Okay, what do these numbers even mean? Well, they're about a little less than a quarter of a pound of force. So on Earth, 1 kilogram of mass has the gravity, because gravity is 10 meters per second squared. 1 kilogram is about 10 times that number that's shown above, or 2.2 pounds of force. So for every 2.2 pounds that you weigh, that's about 10 newtons of weight or force. Because remember, weight is just one type of force. There are many kinds of force. There's gravitational force, which is also known as weight. Your weight is the force of gravity on your body by the earth. And so 1 kilogram of mass on Earth is equivalent to 10 newtons, about 10 newtons. It's actually closer, if you look in the number down below, I said that gravity was about 10 meters per second squared. The actual number, 9.8, it's closer to 9.8. In most textbooks, you'll see 9.8. For the purposes of this course, most of the time you're going to use the rounded number of 10 meters per second squared for the acceleration due to gravity. We distinguish between the acceleration due to gravity, that's how much faster you get as you're falling, from the force of gravity, that's the weight or force of your body moving down due to the Earth's gravitational pull. Okay. So the other unit I mentioned was the dyne. We're not going to use the dyne too much in this course. It's used by some engineers who use a different modified system, the metric system, called the CGS system. That stands for centimeter, gram, second, as their basic units. And then pound is the one you're most familiar with for a unit of force or unit of weight or unit of tension. So tension is another type of force. And you can have tension in cables and strings and ropes, whatever. Okay, so a pound is about a little less than half a kilogram of mass equates to a pound of force on Earth. All right, so force is a vector quantity, just like velocity is, just like acceleration is. Force has a direction. So it has a magnitude, tells you how big it is, and it has a direction, which direction it's pointing in. And we represent any vector with arrows. And the length of the arrow tells you how big the magnitude is, and the direction of the arrow tells you the direction of the vector, of the force or the velocity or whatever vector quantity, whatever vector property we're talking about. So examples of vectors, as I mentioned, force, velocity, acceleration. Things that are not vectors. Speed is only the size of the velocity. It's the magnitude of the velocity. It's called a scalar because it only has size. It doesn't have direction. Also, when we talk about speed, a constant speed in a single direction, well, that's a constant velocity. But a constant speed, if we're going in a circle, we're constantly changing direction. So while that might be constant speed, it's not constant velocity. So therefore, there actually is acceleration in that case. So it's a little tricky concept to get used to because you're used to using English words in one way, and now in physics, we use them in a more defined way. All right, so net force is the combination of all forces that act on the object. So here are a couple examples. In the top example, example 1, we have two 5-Newton forces pulling in the same direction on that block. And they both pull together to form a single 10-Newton force pointing to the right. Well, that makes total sense. If you had two people pulling with the same force, the force is doubled, and you get the new force in the same direction. In example 2, however, we've got the same magnitude forces, but in opposite directions. Well, they're going to cancel each other, and now our net force is 0. And we can calculate this just by subtracting one from the other. If one is bigger than the other, say it was 6 newtons and 5 newtons pointing in the opposite direction, we would say the net force is 1 newton pointing in the direction of the bigger force. So here's an example. A cart is pulled to the right with a force of 15 newtons while being pulled to the left with a force of 20 newtons. The net force on the cart is 5 newtons to the left, 5 newtons to the right, 25 newtons to the left, 25 newtons to the right. Well, you see the left one is pulling opposite the right one, and the left one's a little bigger. So the net force is going to be that difference pointing in the larger force's direction, and we get a 5 Newton force pointing to the left. So the direction of the net force is always the direction of the larger of the two if they are absolutely opposing each other. Here's another example. What's the net force acting on the box? We look at the picture, we see a 5 Newton force pulling to the left, a 10 Newton force pulling to the right. Simply take the difference, and you can see that the difference is a 5 Newton force pointing to the right. So 10 minus 5 is 5 newtons. The bigger force is pointing to the right. So vector quantities, as I mentioned already, have magnitude and direction. We represent them with an arrow, velocity, force, acceleration, and a number of others, momentum. have directions, so they are vector quantities. Scalar quantities have no direction. They just have a size, a magnitude, mass of an object, a volume of an object, the speed of an object. Those are all scalar quantities. So while mass is a scalar quantity, weight is a vector quantity, because weight is a type of force and it's pointing straight down towards the center of the earth. Tension is another type of force. Tensions are forces that are directed along the length of, say, a string or a cable or a wire or a rope or whatever flexible object is being pulled with tension due to forces on it. And so I've shown 3 examples here. You've got little Nelly hanging from 2 rings that are supported by 2 cables attached to the roof. There's a left tension and a right tension. We've got a tug of war on a hill between one team and another, and then we have a rock being supported from the ceiling. And what you have to understand is that every one of these tensions comes in pairs. There are always opposite and equal pairs of forces within whatever rope or cable or string we're looking at, and the tensions are the same all along the length, both in opposite directions. They're pulling, and that's what keeps. We know that because the string or the rope or the cable is taut. It's not flexible and floppy. It's being held straight, and that's how we know that the cable is under tension, and that the tension is the same all the way through. We're going to assume that these ropes and cables have no mass of their own to keep the math simplified in these cases. So assuming that the rope has no negligible mass, no acceleration, the tension is exactly the same everywhere along the length of that rope or the cable. And you'll notice it's the same in both directions everywhere along the length of the cable. That's a little weird to think about, but it is. And we know that because if we put scales, actual spring scales on the rope itself, we'll see the same tension, the same force being pulled at every point along that rope or cable. So here are examples where we're using spring scales. They're actually right in the cable itself, and it's a spring inside a little device that stretches and will move a little marker that will tell you how much force is on it. It might be in pounds, it might be in newtons. Occasionally it's in kilograms, which is a mass unit, but it's just kilograms that have been converted from newtons. And you get these tensions. So in the first case, in all of these cases, we're using a weight that weighs 100 newtons. 100 newtons is about 22.5 pounds, just so you get an idea in the imperial system that you're used to. So in this situation, you see the weight is supported by 1 or 2 cables with these spring scales that will measure the tension at different points in the cables themselves. We also have a couple more complicated examples in Figure 5. It's 2 cables and one's on a pulley, and in Cable 6, it's on one cable, but it's on a pulley that's attached to a weight that weighs a lot. It's a small weight in this picture, but it weighs 10 times as much as the 100 Newton weight. So let's look at the first example. We have a tension. It's being pulled by the 100 Newton weight, so the tension is going to be 100 newtons. That's pretty straightforward. In Figure 2, it's held up by 2 support cables, so the weight is split between the 2, so we get 50-50. And in example 3, if you look at tension 4, it's holding up 100 Newton weight, so that makes sense. It's 100 newtons. But you've got this other spring scale on the same string on the other side of the pulley. Well, the pulley's not changing any forces, it's just changing the direction of the force. And remember, the tension along any single string is exactly the same everywhere along the string, even if it's on the other side of the cable, the pulley. So tension 5 is the same as tension 4. It's the same string. And if you look at Figure 4, I think you already know that tension 6 and 7 are going to be the same, but the question is, are they the same as the total, 100, or are they split 50-50? Well, if you imagine there was only spring scale number 6 we're looking at figure 4, scale number 6 by itself, that would have 100 newtons. There's 100 newtons of force pulling on it. But there's also 100 newtons of force pulling on spring 7. So both of them will register as 7. They're the same cable. You're just measuring the tension in two different places. So don't think of it as the spring that's holding up the tension. It's just measuring the tension at different places on the cable. Figure 5, you have two cables. One's on a pulley, one's not. Well, you're going to split up the weight as long as they're evenly balanced cables. So 8 and 9 will both have 50 newtons, but 10 is on the same string, the same cable as number 8. So it will also be 50 newtons. Don't be fooled by the fact that you see 50 and 50 and 50 and think, well, that's 150. That doesn't match the 100 pulling down. Well, it does, because you only count the two 50s on the left as 150. You're just measuring the same string in two different places. And the last example, you have this big heavy weight on the table that's so heavy that it has friction that's holding the weight from moving. So figure 6 is really the same as figure 3, where you've got the weight attached to the table. It's essentially the same, and we would see 100 newtons on one part of the string and 100 newtons on the other. All right, so the concept of resultant vectors, resultant forces, resultant velocities. Anytime you have vectors, you can add them up if you have more than one vector. So the sum of of two or more vectors is called the resultant vector. It could be a resultant force or resultant velocity, as I just mentioned. And for vectors in the same direction, you just add them up, and it's pretty straightforward. We already did an example of that with the box being pulled by two 5-Newton weights. For vectors in opposite directions, we just subtract them arithmetically. We've done that as well. But what if they're not in the same direction or the opposite directions? What if they're at an angle from each other? Well, we use something called the parallelogram rule. You have two vectors, and you treat them like they're two sides of a parallelogram that you can't see the other two sides of. So you draw the other two sides. One side's parallel to one of the vectors, and one side's parallel to the other of the vectors, and you make them the same lengths, and you end up with this parallelogram. That's the parallelogram rule. Well, how do you know what the resultant vector, what the sum of these two vectors is? Well, if you add, say these were forces or pushes, if you're pushing in the direction of V1 with that size push, and you're pushing in the direction of V2 with that size push, and two people are pushing on a box with those two forces in those two directions at the same time, well, the resultant force will be in this diagonal direction. And you can do this without any math by just drawing the vectors and making a quick and dirty sketch and drawing the diagonal. And you can determine where the resultant vector is and roughly the size of that vector. Now, if you were in a more advanced course, we would actually calculate it, but it uses trigonometry. We're not going to do that here. So vectors at a right angle, your parallelogram is now a rectangle. Well, if it's a rectangle, it's easy to calculate the diagonal. You just use Pythagorean theorem, a squared plus b squared, those are your two vectors, your component vectors, equals c squared. That's the c squared in this case is the resultant vector squared. So the magnitudes of those vectors are just the square of one of the magnitudes plus the square of the other, and then you take the square root of the sum to get the resultant vector's magnitude. We're not going to worry about the resultant vector's diagonal unless it's something simple. If they're both the same magnitude, the diagonal will be at 45 degrees. Otherwise, you need trig to do it, and again, we're not going to do that here. So here's a question for you. Referring to this figure, we've got a figure with a 30 Newton force pointing up, a 40 Newton force pointing to the right, and a diagonal force of 50 Newtons from the rectangle that we formed, from the parallelogram that happens to be rectangular in shape. 50 newtons is the resultant of the 30 and 40 Newton vectors. B, the 30 Newton vector is a component of the 50 Newton vector. C, 40 Newton vector is a component of the 50, or all of the above. Well, I think you can see from the drawing, it's all of the above. By using Pythagorean theorem, you can see that the 50 vector is the vector sum, using Pythagorean theorem, of the 30 and 40 Newton vector. And you can prove that to yourself by taking 30 squared plus 40 squared and showing that it equals 50 squared, or 50 is equal to the square root of 30 squared plus 40 squared. And so that's how you use Pythagorean theorem in this case. So here's another situation with vectors and component vectors that allow you to analyze a situation. So here Nellie Newton is hanging from a rope hanging from two ropes, actually, two cables. She's hanging from this handle that's attached to two cables, and there's tension along each of those cables. So the question is, which side has greater tension? And you might be tempted to say, oh, it's the longer cable. Well, it doesn't work that way, so let's take a look. So there are three forces acting on Nellie. You've got her weight that's pointing straight down. It's always pointing towards the center of the earth. And we know from Newton's second law, which we haven't done yet, that weight, the force of weight, and I use a number of different ways to express force of weight. It might be F sub W, or it might just be W, or force due to gravity, F sub G. It's equal to her mass times gravity. And we're not going to worry about that right now, but you've got the force pointing down. Well, she's not moving, so there must be a force pointing up to keep her in place. And that force is coming from the cables. So we've got a tension along the left cable, and we've got a tension on the right cable. Now, I've not drawn the size of the two tensions to scale. The blue lines could be shorter, they could be longer. They're just drawn there just to show you direction. So how do you figure out how big they are? Well, you have to do a little analysis. First, you realize she's in equilibrium, which means her velocity isn't changing. In this case, she's just standing still, which means the force up has to be exactly the same as her weight force down. So we know there's a force pointing up that's the same magnitude in the opposite direction. So where did this come from? It came from adding up the two tension forces. And the two tension forces, how do you figure that out? Well, you use the parallelogram rule backwards. You know the diagonal, and now you create a parallelogram that matches that diagonal. Well, the sides have to be parallel to the two cables because each tension is in the cable. It's along the length of the cable. So you can make parallelogram where two of the sides are parallel to one cable and two of the sides are parallel to the other. And that takes a little practice to do, but once you do that, you just move those green vectors so that they match along the lines of the cables themselves. So I move the right green vector down to the left cable, and I move the left green vector down to the right blue vector, and you can see that the left tension is actually less than the right tension on her, and that when you add these three forces up on her, the tension to the left, the tension to the right, and right upward, and the weight down, those three tensions pulled together. If you had three people pulling in three directions like that with those size vectors, whatever you're pulling in the middle will not move. The net force is zero. So here's a picture of Burl Gray. This is a friend and former teacher of the author of the textbook, and he's holding up a bag of flour with a spring scale, and this is a pretty bulky spring scale so that you can see the value on it, and you can see the tension force in the string is pulling up to keep the gravity force of the bag in order to cancel those two forces so the bag's not moving anywhere. So the two forces have to be equal magnitude, equal size, and opposite in direction. When they add together, they cancel to zero. We call that static equilibrium. There are two kinds of equilibrium, two kinds of what we call mechanical equilibrium: static equilibrium and dynamic equilibrium. Static is when the object is not moving at all from your point of view. And dynamic equilibrium is when it's moving, but it's moving at a constant velocity. We'll talk about that in a minute. So this bag is at rest. So the equilibrium rule says the vector sum of all the forces on a non-accelerating object, in other words, it's either standing still or it's moving at a constant speed in a constant direction. There is, in that case, the vector sum of the forces has to equal zero, and vice versa. If the forces are zero, it can't be accelerating. It's either dead stopped or it's moving at a constant speed in a constant direction. And we call that, we write that mathematically as the sum of F, the forces, equals 0. If you're not familiar with that symbol, that's the sigma symbol in mathematics. It means the sum of all the different versions of whatever follows it. So it's the sum of all the forces equals 0. So here's a situation where you have Burl on the left and Paul, the author, on the right, standing on a painting scaffold, and you've got the scaffold supported by 2 cables. So there are three force vectors pointing down: the weight of Burl, the weight of Paul, and the weight of the scaffold, which we have put in the center of weight, the center of mass of the board, pointing straight down. But they're all pointing straight down. But these guys aren't moving. We know that. We can see that they're not moving, and therefore the sum of the forces must be 0. So that tells us the forces pointing straight up have to sum to the opposite and equal value of the forces pointing down. In other words, if we took the 2 upward forces and subtracted the 3 downward forces, we would get 0. So we say the forces cancel to 0. They're in equilibrium. The net force is 0. So the equilibrium rule, the sum of the forces equals 0, applies to vector quantities, scalar quantities, both or neither. Well, it applies to vector quantities. If you were looking at masses, masses are not vector quantities. They're scalar. They just have a size. If you have 2 masses, you're never going to cancel out masses no matter what you do with these masses. They'll just add up. You keep adding them and adding them as long as you're adding masses. Whereas forces, you could have one in this direction, one in this direction, and they will cancel each other. So it really only applies to vector quantities. So vector addition accounts for the positive and negative and weird directions, diagonal directions of vector properties. 2 in the opposite direction can cancel to 0. 2 in a bunch of directions could also cancel to 0. We have another kind of force called the support force. And when that support force is from a surface pointing perpendicularly up from the surface, we call that a normal force. Usually I'll call it a normal force, but a normal force is the most common kind of support force. And these are forces that keep objects that are sitting on a table or a person standing on the floor from going through the floor or going through the table. If those forces weren't there, gravity would pull you right to the center of the earth. But gravity doesn't. You know you can stand still. That means your weight down has to be countered by something pointing straight up. And that is what we call a support force or a normal force. And so it's frequently, but not always, in the opposite direction of the weight and in the same magnitude. But if you have slanted surfaces, things are changed, and if everything's moving, accelerating up or accelerating down, those differences in sizes will also change. But think of it as a support from the whatever it's sitting on. So these are what keep it from passing through the floor right to the center of the earth. Support force never pushes harder than is necessary to keep you from going through the earth or a table or whatever you're supported on. So if it's just sitting on a flat surface, the normal force is exactly equal but in opposite direction of the weight force. And I've shown 2 different ways of writing normal. Normal sometimes written as n, sometimes F sub n. Weight sometimes written as F as W or F sub G for gravity or F sub W for weight. So they have to be equal and opposite. And the support force will increase its force depending on how much weight is pushing down. So it only adds just enough to keep it from going through the floor. Well, where does this come from? Well, it comes from the fact that the book is compressing atoms in the table, or your body is compressing atoms in the floor, and the compressed atoms are pushing back at you to keep you from compressing anymore. And that accounts for the support force, in this case, the normal force. So if you have a book on a table, we've already talked about that. The same goes if you're pressing on a spring and you're just holding the spring down. Since you're not moving, but you're pushing down with a certain force when it's not moving, there must be an equal and opposite force pushing up, and that would be the support force. It's the force from the spring itself in this case. All right, so you stand on 2 bathroom scales with 1 foot on each scale, and your weight is evenly distributed. This is important because you could step on 2 scales and lean one way or the other, and your weight won't be evenly distributed. But in this case, it's evenly distributed. What will each scale read? Your weight, half your weight, 0, or more than your weight? Well, I think we've already talked about this with the tensions. It's going to show half your weight on each scale. Each scale is supporting half your weight. So if you're at rest, your net forces are 0. So your weight going down has to be supported by 2 support forces going up in the scales. So each scale will support half of your weight. So I mentioned before, equilibrium, more technically called the mechanical equilibrium, is a state of no change, no net force, no net acceleration. And that comes in two basic flavors: static equilibrium and dynamic equilibrium. Static means the forces cancel and the object is at rest, no movement at all. A hockey puck just sitting on the ice, that's static equilibrium. Dynamic forces, the forces still cancel, but the object has a constant motion or velocity. That is okay. Constant motion or velocity still means no net force. And the reason why it means no net force is their frame of reference issues. What if you're watching a train going by at a constant rate? Well, to you, the train is moving and every object on the train is moving. But if you're in the train, all the objects in the train are standing still because you're moving with them. So it's a frame of reference, and that's why we don't make a lot of distinction between static equilibrium and dynamic equilibrium in our calculations. They both count as equilibrium and therefore no net forces. So an example would be the hockey puck just sliding across the ice. Now you had to impart a force on the hockey puck to get it moving. So while the stick is actually in contact with the hockey puck, there's a force. It's accelerating it. But the second the stick leaves the hockey puck, the puck is moving at a constant velocity at that point. So equilibrium test, when something does not undergo a change in motion, really a change in velocity, that is equilibrium. So a crate at rest is in static equilibrium, no change in motion. When pushed at a constant speed, it's in dynamic equilibrium. There's still no change in motion. It's moving constantly in the same direction. So a bowling ball is in equilibrium when it is at rest, when it moves steadily in a straight line path, both or neither. Well, we've been talking about this. It's both, because A, at rest, that's static equilibrium, and B, moving steadily in a straight path, that's a constant velocity, that's dynamic equilibrium. So equilibrium just means no change in the motion, either at rest, static, or in motion, constant speed and constant direction, dynamic equilibrium. You push a crate at a steady speed in a straight line. Right away you hear steady speed in a straight line, think no net forces, no acceleration. Net force is 0, net acceleration is 0, no change in speed or direction. If a kinetic friction force is 70 newtons, how much force must you apply? Okay, what is kinetic friction force? Well, friction force, there are forces of friction. Friction is a resistant force. So friction will always be a force between objects that are rubbing against one another in the opposite direction of whichever way movement is occurring. So if movement's going this way, the friction will, by definition, will be this way. If movement's going this way, friction by definition will be going this way or this way. It's always in the opposite direction of movement. Friction never helps you move in the same direction. It only slows you down in moving in the right direction. And it's a force. It will actually change your velocity. Okay? So their friction has to be overcome in order to get movement started, and it has to be overcome in order to keep movement occurring. And there are two different kinds of friction. Static friction, that friction to get that box first started. And kinetic friction, to keep moving that box over the floor, because there's always going to be friction. Now, why are these different? Well, it's a little harder to get an object moving in the beginning, so static friction is always slightly greater than kinetic. And the reason is the molecules of the two surfaces are kind of sitting inside one another. They're kind of interlocked like this, And to get that first push going, you have to kind of pop them out, and that's a little harder. But once they're moving, they can move over top of the surfaces of one another, and so the kinetic friction is usually a little less than the static friction. But we're going to say her kinetic friction is 75 newtons. The floor is providing that much force against the box. So what does she have to apply to make a steady speed in a straight line? More than 75, less than 75, or equal to 75 newtons, or we don't have enough information. Well, it's steady speed. That means her net force will be 0, which means the kinetic force of 75 newtons has to be exactly compensated for by the applied force, the push force from the little girl of 75 newtons in order to get the net force to be 0. You have to apply exactly the same amount if you have constant velocity or no velocity. All right, so Copernicus proposed that the Earth was moving around the sun. They used to believe what was called the Ptolemaic era. Ptolemy was somebody who studied science in ancient Greece in the BC era, and he postulated that the Earth was in the center of the solar system, in the center of the universe, even at that time. And so a lot of people didn't believe Copernicus, but his information really fit what they were seeing with the planets moving around and the sun moving around in the sky. But the question they had was, well, if the Earth is moving, how come things aren't flying off? How can a bird swoop down from a branch and have the Earth not fly out from under it? I mean, the Earth is moving at about 30 kilometers per second. We know that now. That's about 18.5 miles per second. So why is the bird able to get the worm on the ground if the Earth is just flying out from under it at 30 kilometers per second? Well, the reason is the bird's moving at 30 kilometers per second as well. Everything on Earth is moving at 30 kilometers per second with the Earth. We're all moving together. That is what inertia is. We all have the same movement. And that movement has to be overcome in order to change it. All right. So we're already moving. We already have that momentum as well of the movement of Earth, and that's why we don't go flying off when we jump up in the air. So you're riding in a vehicle at a steady speed and direction. Now that should say direction, not director. And toss a coin straight up. Where will the coin land? Behind you, ahead of you, in your hand? Not enough information. Well, I think all of you have done something like this in the car. Throw something up. It comes right back. It doesn't go anywhere. And that's because the coin has inertia. The coin is already moving with the same speed as the car in the x direction, in the horizontal direction, moving forward. So when you throw it up, all you're doing is adding movement in the vertical direction. The coin will come back down, or the toy or the ball or whatever you're throwing up and down. They're all moving. We're all moving together. You just don't see it because your frame of reference is that everything's standing still. If somebody outside of the car was watching you, they would see you and the coin moving together at whatever it is, 60 miles an hour. So that's why it always lands on your hand, even when as long as you're moving in a steady speed in a constant direction, in other words, a constant velocity. If you're turning and you do that, the coin's not going to land in your hand. And with that, we're going to end the unit. Thank you very much.